So I have told you now that we can somehow generalize our setting of a normed vector space or metric space to a topological space by just taking the information about open sets. But of course, I mean, I should be more precise on this and really convince you that this is really meaningful and not just nonsense, arbitrariness, and that we are not losing too much. In particular, I mean, everything we are interested in, we should be able to formulate in terms of open sets in the setting of our metric spaces, and then of course we can also use those reformulations as maybe characterizations or definitions in the most general setting. And of course we can use those reformulations also maybe in proofs we are going to do. So I mean from our point of view of the Stone-Weierstrass, maybe it's not so important to talk about the most general topological spaces, but it's really important that we have this reformulation of compactness in terms of open sets. Good, but anyhow, so I mean, let me give you two examples of how this reformulation is done. Maybe one is to reformulate the notion of a continuous function in terms of open sets, and then most important for us, to reformulate compactness in this setting. Okay, so but let me start with a continuous function. So I mean, this is a theorem. Of course, in the setting of normed vector spaces or metric spaces, we have the notion of continuity and compactness, and so we want to reformulate it in terms of the open sets. Okay, so for continuity, so assume we have two spaces, x and y, and both have a metric, so we can measure distances there. So this should be metric spaces. For example, normed vector spaces. Yeah, okay. And then I consider a function from x to y. And I want it to be continuous. So what does it mean? Okay, then the following are equivalent. Of course, we know what continuity means. So namely, and that's what we call continuous up to now. So f is continuous. So this means whenever I have a sequence of arguments which converges, then the sequence of the function applied to this argument should also converge, and it should converge to the function to f of the limit. So this means if xn converges to x, so convergence here in this metric space, and we have a distance, so we know what convergence means. Then, if we apply f to it, then we get the convergence of f of xn to f of x. So the limit of f of xn is f of the limit of the xn's. That's our usual definition of continuity. Okay, but then one can reformulate this, and okay, I mean, in principle you should have seen such things, for example, in analysis 2, real analysis 2. But anyhow, so I mean, it is in any case true that I can also write this in terms of open sets by just saying that the pre-image of an open set is open. And that's an equivalent characterization for continuity. So this means this here is equivalent to saying that for each open set in U, in Y, so if U is an open set in Y, and Y has a metric, and of course it corresponding to this, it has a topology, given exactly in this form, that we say what an open set is there. And so for each such open set, we can look on its pre-image. So those are the elements in X which are mapped into this set under F. So it's pre-image, which we denote by F to the minus 1 of U. So those are by definition the elements in X which go to U under the mapping F. So this is a subset of X, and I'm claiming this is also open. Of course, in the topology coming from the metric on X. Okay, so that's an equivalent characterization. And then if we have a topological space where we only have a topology and no metric or so, then actually this here is maybe a good, or this serves as a definition of of a continuous mapping in a general topological setting. So that's really a good definition, which captures all the things which we can do in metric spaces with continuous functions. Good. Okay, but maybe even more important is what is compactness in terms of open sets. And that's also a very basic and famous theorem, which you should also have seen in analysis 2. Namely, that's a Borel-Lebesgue characterization of compact sets. So this is a theorem which usually is attributed to Borel and Lebesgue. Okay, and of course, okay, I mean it's again in a setting of a metric space where we have a notion of compactness with subsequences, where it gives us a reformulation in terms of open sets. So let us look again at a metric space. X is our metric space. So I'm not writing down the metric, but it's clear that this comes with the metric space. Okay, and I consider a subset of X, and I want to know is this compact or not. And then the following are equivalent. So namely, first, it is compact in a sense which we used up to now, namely by saying that every sequence in this set has a convergent subsequence. That's what we defined as compactness, and which we used at many places up to now. So, and maybe in general, in order to maybe distinguish it from things in a more general setting, this is also called sequentially compact, because it's characterization in terms of sequences. So this is A is sequentially compact, but that's what we called compact up to now. And so maybe let me recall, what do I mean with this? I mean that every sequence in the set A, every sequence in A, so this means every sequence which has values in the point A, we are interested in convergence of sequences. Okay, such an arbitrary sequence doesn't have to converge, but if the set is compact, then at least the subsequence converges. So every sequence in A has a convergent subsequence, and actually the limit should also be in A, as a convergent subsequence with limit in A. So that's the notion of compactness, which we used up to now, and which is a very useful concept. Good. Okay, but then the question is, of course, how can we characterize that a set is compact? And of course, in finite dimensions, we had Heine-Borel. It must be closed and bounded in R to the n. Then for continuous functions on, let's say, the interval 0 to 1, we had Ascoli, which also gives us a characterization. But here we want to understand it really in generality for all metric spaces. And in principle, what you need, I mean, if you're thinking back how in finite dimensions this is proved that you have a convergent subsequence, this is this is this Bolzano-Weierstrass argument. You have in your set, you have a sequence, then you divide your set into two parts, into two halves, and then at least infinitely many points of your sequence must be in one of them. Okay, then you're looking on this half and you divide it into two again, and again you must find infinitely many elements from a sequence in one of those halves, and you continue in this way. And this allows you to construct a subsequence. And if you want to do this argument in a general setting, so what you need is actually that you can divide the set which you have into a finite number of small, let's say, balls. Okay, or small intervals or balls. Okay, so that you can make the balls smaller and smaller, but that you can cover your whole set by finitely many of them, so that you can can be sure that at least one of them must contain infinite number of your sequence. And then you are looking on this one ball, and again, then you can cover this ball by smaller balls. But again, a finite number. So again, you find infinitely many numbers in one of them. Okay, and so this is exactly what you need, and that's exactly a criterion which allows you to imitate the proof of Bolzano-Weierstrass and see that you find such a convergent subsequence. Okay, and so what you need is this what is called totally bounded, namely that you can cover your set for each given radius by a finite number of balls of this radius. Okay, and this gives you a subsequence, which is a Cauchy sequence. Okay, and then that it converges to something in a set. Of course, this requires that your set is complete. Okay, so you need to have this here in particular, that you have a limit, is you need completeness. This just means that really, if you have a Cauchy sequence, then it converges, and the arguments you are doing are arguments which provide you with a Cauchy sequence. Okay, so you need the completeness, but then you also need this property, this covering property, namely that your set is totally bounded. And with this, we mean that for any radius, for any epsilon bigger than 0, you can cover your set with a finite number of balls of this radius. Of course, if you make the radius smaller and smaller, you need more and more balls, but in any case, you can do it with a finite number. And then, then this is essentially enough to apply this Bolzano-Weierstrass argument, namely you can cover your set by such a finite number, and then your sequence, which you are considering, infinitely many of those guys must be in one of these balls, and then you continue with this ball. Okay, but so what you need is this totally boundedness, so that for each epsilon bigger than 0, you have finitely many points x1 up to xn. So you have an n and finally many such points, such that your set A, the set of which you want to know whether it's compact or not, that this can be covered by the union of the balls about the point xi with radius epsilon. And this is here a finite covering. Okay, so this is essentially, I mean, this is the general version of what you have in Heine-Borel, namely that you need, in Heine-Borel, you need closed and you need bounded. And closed is here replaced by complete, because you are not a priori a subset of something. I mean, if you are in R to the n, then a closed subset of R to the n is complete. But the boundedness is more, I mean, it's not just that you bound things by one ball, but you must have this kind of boundedness that you can cover it by a finite number of balls of any given size. Yeah, okay, so this is already quite nice, but then you can also make this more general, namely, of course, here you require that you have balls of a given size, and then you have finitely many which are enough. But of course you can also try to cover your set with balls of different sizes, and then of course you might not be able to cover it with finitely many. If you make the sizes smaller and smaller, you might need infinitely many to cover, you might not be able to cover everything. Okay, but, and that maybe is the most crucial thing, if you are able to find coverings of your set by open sets, and maybe you have infinitely many, then actually finitely many are enough. Okay, so that's the point 3, which is for us here the most important and the most general, namely that you are not trying to cover your set with balls of a given radius, but you are just looking on any covering of your set by not even necessarily balls. I mean, here I have open balls, but now I just take arbitrary open sets. So if I have any covering of my set A by open sets, so every open cover of A, so actually I don't need infinitely many of those guys. I mean, this open cover might be very big. It can be infinite, uncountably infinite, but the point is I only need a finite number of the elements from this cover. So every open cover of A has a finite subcover. Okay, maybe should say more precisely. So let's say an open cover. So this means I have a collection of open sets which are indexed by an index set I, and this I can be arbitrary. It can be a very large index set. It can be the real numbers, and each of them is open. So all the UIs are open, and this UI, if I take their union over all this I in this index set I, then they cover my set A. So if I find such an open cover, then actually I don't need this very big covering, but actually I can choose, I find a finite number of elements in this cover which are enough to cover the set A. So that's the conclusion here, that actually I only need finitely many guys of this cover. So finitely many indices I1 up to In in my index set, such that I take the corresponding U's, then they cover already A. So such that A is actually already contained in the union of UI1 with UI2 and so on with UIN. Okay, and now you see this, and this is really equivalent. So this guy here, and this is something which really uses only open sets. I mean, here in 2, I have still talked about balls. So I use special open sets which are given by balls. But then here in part 3, I can just get away from the balls and just talk about open sets which cover my set A, and then I only need finitely many of them. Okay, and that's a characterization which really just uses the topology, just the sets, the open sets. And that is also, in a general topological space, the correct definition of compactness. So 3 here is really how one usually defines the notion of compactness in a very general situation. And then 1, you might also still have 1, but that is not necessarily the same in a very general situation. And then 1 is called sequentially compact. Okay, but of course, important for us is that in the metric setting, it's the same. Okay, so instead of looking for subsequences of a sequence, we can also look or try to use the fact that every cover has a finite subcover, and that's what we are going to use later if we will prove Stone-Weierstrass. So that's our. I mean, we are not looking on convergent subsequences of given sequences, but we will use this property that we have a finite cover of every open cover. Okay, and maybe you should think of this as a general procedure or something which allows you to go over from local information to global information. Because I mean, these open sets usually, I mean, you might get them or define them by having a property which is locally valid. So you have something at a point X, and maybe this is also valid in a small neighborhood. So for each point X, you can find a small neighborhood where you have some property, some continuity or some Lipschitz constants or whatever. And so, I mean, for each point, you find this neighborhood, and then, of course, if you take all these neighborhoods of all points together, this covers your set. But of course, you have now a covering by an infinite number of open sets. Okay, but if your set is compact, then this tells you actually you can restrict to a finite cover. So you only have to look on a finite number of points and their neighborhoods, and they cover everything. And then you have a finite number of properties which are valid locally, but usually if you have a finite number of local properties, you can make a global property out of this by taking the minimum or so of the constants which are involved. Okay, so I mean, going locally to globally, if you only have a finite number of of sets, this is easy. Huh? I mean, on this side, you couldn't do this. You have locally, for each point, you have something locally, but if you want to go globally and you take the infimum over all constants which you have in your local conditions, then this infimum might just be 0. Huh? So your property disappears. So, okay, but if you take it for a finite number, then it will not disappear. Maybe the constants will become a bit worse, but okay, you don't care about this. At least you have something. And so you can really go over from local to global properties. And that's really one of the main points, very important points, and how you use compactness very often. Okay, good. But later in the proof of our Stone-Weierstrass, we will see exactly an instance of this.